Okay, this is the number 14, the studies of the lecture in digital image processing. Today, I would like to talk about Hadamard, they say Hadamard, but Hadamard Transform. And this is a two-dimensional, this is one-dimensional Hadamard Transform. For one dimension, the kernel is like this. And if the kernel is gxu is 1 over n minus 1 to power summation of bix biu. So this bi is the ith bit in binary representation of x. So it should be, for instance, it should be 0 or 1, and then multiplication, and then addition here is performed all based on module 2. So the result will be 0 or 1. If it is 0, the minus power to 0 is plus 1, result is plus 1. And if it is 1, the resultant power of minus 1 is minus 1. So it's plus minus of the component. So let's see I show the full transformation here with that kernel. I told you this is the kernel. For instance, you have one-dimensional function fx. The Hadamard transform will be hu with this. And then the inverse transform would be this, which this is h, almost the same. And then just fx return from hu can return to fx, or different x from 0 to n minus 1 and so on. But for two-dimensional, this is for one dimension. For the two-dimensional, just x, we have xy and uv. So the kernel would be bix biu plus biy bib, and the same. And the inverse kernel is like h. And then for two-dimensional, I show you here. This is for two-dimensional. There is double summation of over x and over y from 0 to n, large n minus 1. And then this is for kernel, for the transformation. Page 138 of Gonzalez. So this is the inverse of the two-dimensional. And it is because this is also separable transform. So gxy and uv is g1xu and g1yu. So it is similar. So it is 1 over root n and so, and then 1 over root. So double, they are both set, so they can be separable computing. And for n200, they have something to show here, and then as in FFT, also we can perform that. But the most important part is this, that if you can make the successive doubling of the Hadamard transform by this. For instance, if H, the matrix form, in matrix form, for instance, H2, as I said, in general matrix for transformation, H2, the kernel of the H2 Hadamard transform is 1, 1, 1, minus 1. For Hn can be recursively obtained from the H2n from Hn. So if you put this to this one, this one, this one, and minus here. So from 2 to 4, 4 to 8, and double, for n, from n, you can obtain 2n. So that would be the general form of the multi-dimensional Hadamard transform, and the kernel for n equal 8 is shown here, x from 0 to 7, and the output u is from 0 to 1. As we see, the component of the kernel is all plus for the 0, x from 0 to 7. For u0 is all positive. For 1 is all the frequency, highest frequency plus minus, or plus minus plus minus. So its highest frequency is in the second place, which is not in order. So that is not ordered Hadamard. And so on. You can see the variation of the plus minus for double, or 4 plus here, 4 minus here, or 1 plus minus, and 2 minus in the middle, and so on. And at last, plus and double minus, plus minus, and then double plus minus. This is the kernel computation. That for the one dimension. This is of course for the one dimension. And then this is the example that it shows you for from 2, they obtain from 2 to minus, from 2 to, from 2, H2, we obtain H4 kernel like this. From H4, we obtain the H8, something like this. This is matrix 4. Also, if you want, this is not order Hadamard. So if you want the order Hadamard, it is the, as I said, it is, if you want the ordered Hadamard, which is the highest frequency here, I will tell you this. For ordered Hadamard transform, instead of BIX, BIY, BIU, we put BIX, PIU, not PIU, but PIU. This P is obtained from B. From B0, U is Bn minus 1U, B1, P1, U is Bn minus 1U plus Bn minus 2U. This all is plus minus, is 0 or 1. So that is why it is the bit number. And so the all summation are obtained based on modulo 2. So this is we have from 0 to P0 to Pn minus 1, which is back to B1 to B0. And so this kind of make the with this kernel, instead of B, we use P here. With this kernel, we can, where recursive is this one. We can. This is like a gray code. This with P is a gray code in the one dimension. For 2 dimension, I will tell you. So this is the ordered Hadamard. So if you put ordered Hadamard, let me see. Because I couldn't show the camera here, so you can see my face only. So this is 1 dimension, as you see, in order, instead of using BIX, BIY, we use BIX, PIU, PIY, PIU. And then, so from 0 is marked the very constant value, all plus. For second spectrum or frequency is plus and minus 4. Second, for the, well, third is here 2, number 2 is 2 minus 4, and plus. So, and then gradually the frequency getting higher and higher, variation of the plus minus, and at last the highest frequency, like Fourier transform, is highest frequency here. So on 7 component in the frequency, I mean Hadamard transform is plus minus. This is because it is ordered Hadamard transform. And then I can show you the two-dimensional form if I can find here. Well, two-dimensional form is this with the ordered Hadamard, just instead of P BIU, we say PIU and PIV for two dimension. This is the Hadamard transform, and this is inverse Hadamard transform. And then here is the if you put your image pixel 4 by 4 pixel over this uh, coefficient map, all white is 4 pixels or plus. Black is minus. So it is all plus is all adding all component of the 4 by 4. Here is 4 by 4 pixel. So you are adding for the first 0 and 0, for 0, 0, and for 0 and 1, you have plus here and then minus here for horizontal line, and then so on. So gradually frequency getting higher in horizontal, and this is in vertical getting higher like this, and then go to maximum frequency obtained at the last. So this is two-dimensional ordered Hadamard transform in the pixel form if you want to compute. I think I will stop here because I cannot show camera here, so by handwriting, but almost same. So just I would like to show you this also. Let's show you this or this Walsh transform. So let's go to I want to show the this one. Okay, next page is this one. I want to show the okay. This is Hadamard transform. I want to show in how to say the PowerPoint or PDF form. This is the kernel of the Hadamard transform, as I said here, and the Hadamard transform in one dimension is here, and then so it's kernel and then inverse transform of Hadamard, and for two-dimensional, as I said, is here, but this is not ordered two-dimensional, and for inverse Fourier transform, and so on. And then it is separable, as I said here, it is separable, so you can separate the kernel of Hadamard. And this is the non-ordered Hadamard transform in one dimension, so the highest frequency occur in one, frequency one, dot at last. And then let's go to next is here. So if you want to use matrix form for N2, the kernel H2 is 1, 1, 1, minus 1. So you can obtain 2n from n by just putting this as I show you the example. So as you see here, the number of the changes or sequence or frequency is obtained at here for H8, for instance, 0, 7, 3, 4, 1, 6, 2, 5. You can find from here. This is 0, 7, 2, this. So this is the number of the change. 0, 7, 3, 4, 1, 6. So highest frequency obtained here. And then if you want to put the order, you can use P. P is defined by the gray code like this. And then this is recursive form for one dimension. And then for two dimensions like this. And then one dimension. And then how it look like one change is here, two changes here, three changes, four, and last change is at last. This is seven change here. So maximum frequency. That is why it is order Hadamard. And this is the if you want to show it in the kernel in two two dimension. So this is pixel 4 by 4 pixel of the picture over to this. This is coefficient all plus, and this is for black is minus. So adding all component is the 0 0. Adding horizontal plus and minus, then become U0 V1, and so it's horizontal high frequency and this vertical high frequency. The maximum frequency is here. So later, this is the Hadamard transform, and for now I will finish this because I cannot show the camera here. I have some problem, but I don't know why. And stop the sharing and stop sharing and recording here. And thank you very much.